Hello and welcome to the Critical Design Review for SAFE-T, the secure anti-theft flexible engineered taillight, which now also includes a headlight and turn signals. Our group is composed of 4 members, 2 electrical engineers, Jonathan Diaz and Jay Kersey, along with 2 computer engineers, Paul Wilson and myself. The motivation behind the project is the large number of preventable bicyclist fatalities which occur at nighttime. These may be prevented or decreased with the addition of proper lighting, which will not only allow the bicyclist to more clearly see their environment, but also allow them to be seen by motorists. This product efficiently combines multiple aspects of bike safety with theft deterrence and greater bicyclist visibility. These are our requirements. The application, which will be used to control the product, will be available on both major mobile operating systems, iOS and Android, and will be Bluetooth compatible in order to communicate with the microcontroller. The maximum size and RAM usage of the application are limited in order to decrease its footprint. The hardware requirements are such that the product is USB rechargeable while providing ample lighting, which is visible from a distance, while still allowing a lengthy operating time. Further, protection from the elements is vital because of the wide array of environments which our product may be used. And lastly, the alarm must be audible from a reasonable distance in order to increase theft deterrence. These are our goals and objectives. Overall, we want to create a viable product for bicyclists that increase their safety while being small and portable. The product should be easily affixable so that any consumer may purchase the product and attach it to their bicycle very quickly. It must be Bluetooth capable in order to communicate with the user's smartphone while also having a long battery life and a large battery capacity in order to power the head, tail, and signal lights, which will all be remotely controllable through the app and will have adjustable brightness. This is our system diagram. You can see that all of the sensors communicate with the microcontroller, and the microcontroller will send out control signals to the LEDs in order to adjust brightness or enable and disable. The mobile app and the microcontroller will communicate over Bluetooth as previously stated in order to exchange control signals or to send battery status updates. Onto our software design. This is our software block diagram. Here you can see that the control signals sent to the microcontroller will include button input if we have a physical control box, along with sensor signals, which will then be processed, and depending on which sensor sends the signal, the alarm may be activated or the lighting may change, which will also send a signal to the app to update the UI. Now, the mobile app will receive and send control signals to the microcontroller, which will turn on and off the lighting, adjust the brightness, enable the turn signals, and control the alarm. This is our UI design, which is quite simple and intuitive. Each button shows an indicator as to whether or not the light is on and will be named in order to show the user what light they're activating. And here we can see whether or not the alarm is on as well. And underneath the head and tail lights, we can see that once they're turned on, a brightness slider will also be enabled to allow the user to adjust the brightness of that light. Now when the alarm is triggered, a screen will pop up saying alert, alarm triggered, and this will allow the user to reset the alarm. To the right, we can see that the turn signal indicator is denoted by an alternatively flashing button, the left and right arrows at the bottom of the screen. I'm now going to turn it over to Paul.
There are many ways to create the optional mobile application for the safety module. Since we are targeting two specific operating systems, iOS and Android, we have to consider the best approach to make a reliable application. We considered writing applications in purely the native code with the software development kits provided by the operating system vendors. However, this is large in scope and is very difficult for a small team to manage. So we considered mainly two alternatives: an application built with web technologies or an application built with cross-platform third-party SDKs that abstract the common features of the two target environments. We decided against using web technologies because we needed access to some core components of the hardware, which web technologies do not easily support or even handle. Hence, we decided to go with the third-party libraries to create the mobile application. Our three main candidates for the SDKs to use were React Native, Flutter, and Xamarin. All three of them are widely used by many developers. React Native is a user interface software development framework for developing applications that run natively on the operating system, unlike the React framework, which is used for creating web UI components. Flutter is very similar to React Native, except it does not use native components for its UI. It instead renders the UI components with a graphics library. Flutter is less mature than React Native and also requires the use of the Dart programming language. Unlike React Native and Flutter, Xamarin is a complete SDK for creating native multi-platform applications. The SDK requires the use of the C# programming language and XAML for the UI. We decided to go with React Native mainly because the team is most experienced with it, and JavaScript, the language that it uses. Now I will be discussing the MCU software, which is the most important software component of this project. We wanted something simple yet reliable for managing the various components of the safety module. We also wanted support for concurrency in the microcontroller in order to effectively support the mobile application. We decided to go with the ESP32 for these reasons and for other reasons as well, which will be detailed in the hardware design section of this presentation. We considered writing our own firmware for the microcontroller module, which would suit best for our needs. However, this is unrealistic as we are also writing a mobile application for the project. Instead, we decided to go with an existing firmware. Our main candidates were NodeMCU, Arduino, and MicroPython. We decided to go with NodeMCU because of its general stability and popularity in the ESP family of chips, and the ease of error handling in interpreted languages like Lua. Our wireless communication system between the MCU and the mobile app had to be designed with the use cases in mind. The ESP32 supports both Bluetooth and Wi-Fi, which allowed us to pick either of them. We decided to go with Bluetooth over Wi-Fi, mainly because of the range of the Bluetooth, which would allow the user of the product to arm or disarm the alarm over larger distances. We also did not require the bandwidth of the Wi-Fi protocols, so this was an easy decision to make. We decided to go with the MQTT protocol over the HTTP, mainly because of MQTT's simplicity. One thing we had to consider is the use of TCP/IP over Bluetooth, which requires a gateway. The decision to use MQTT is beneficial here because it is not strictly tied to TCP/IP, unlike HTTP. We have and expect to face some challenges while developing software for this project. We decided to go with third-party SDKs to develop our mobile app. This means some of the operating system-specific features cannot be programmed with them. These libraries do not have the level of support and documentation the native SDKs do. React Native is a UI library, which means we have to either write native code for the components like location, Bluetooth, or rely on third-party libraries that add this capability to React Native. With the MCU software, we are more concerned about the memory restrictions, since we are running an interpreter to run Lua code. We are also worried about the potential lack of libraries, which would result in us extending the firmware, which in turn leads to storage concerns.
Hello, my name is Jonathan Diaz and I'm the electrical engineer for this project, and I'll be covering part of the hardware design. Here is the schematic that was designed for the project. This schematic together is the design of the microcontroller board. At the top left of the schematic is the microcontroller, specifically the ESP32C3, which is an SoC. Below the microcontroller is the voltage regulator that will be converting 12 volts to 3.3 volts and an output steady current of 0.5 amps. Reason behind the two values is because that is what was specified for the ESP32C3 in its datasheet. To the right of the voltage regulator is the USB Type-C connector, which will primarily be used for programming the microcontroller, and above the USB are the headers, which will be used for easy accessibility of the ESP32C3 GPIO pins. Here's our first design for our microcontroller board. Everything was designed accordingly to reduce noise and have easy accessibility. So for the PCB design, particularly the microcontroller selection, we needed to select a microcontroller that is capable of being used as an LED pulse width modulation controller, so that LEDs such as the headlight can have brightness options for various outdoor visibility, such as nighttime with no street lights. We also need to be able to use a microcontroller as an alarm system, which our project will consist of. This means having simple GPIO pins or GPIO connections to communicate with a physical alarm, and sensors for theft detection. Bluetooth communication is also essential for the mobile app control for LEDs and arming or disarming the alarm, which our microcontroller needs to be able to also support. And lastly, we needed simple communication with an RFID module to physically arm and disarm the alarm system for those who wish not to use our mobile app or don't carry phones on bicycle rides. So the team decided to go with the ESP32C3 for the cost and flexibility on the communication protocols, such as the fact that it supports UART, JTAG, I2C, SPI, all of those communication protocols, and has more than enough GPIO pins for our project needs. The voltage regulator selected for the PCB design needed to be specific in regards to the input voltage and output voltage, output current, as well as a consideration for PCB space, meaning small footprint. Specifically, the input voltage needs to be able to handle anywhere from 5 to 12 volts. This is due to the USB connections being 5 volts typically, and the 12 volts is the incoming voltage from our selected power supply, which is a rechargeable 12 volt battery. The output voltage needs to be 3.3 since that is what the MCU requires, specifically the ESP32C3 based on its data sheet, as well as the output current needs to be 0.5 amps, again because of that's what the ESP32C3 can handle. Lastly, a small footprint to minimize any spacing issue with our hardware due to wanting the overall project not being a hinder to a bicyclist's mobility. So with all of this in mind, we chose the LM2574 3.3 NOBP, which, as shown right on the table for its specifications, can handle voltages up to 40 volts and can output voltages 1.23 volts to 37 volts, and can output a steady fixed current of 0.5 amps. There were many other voltage regulators, however, due to the chip shortage, we ended up with a selection for our voltage regulator. Now for the lighting system, which will consist of the headlight, the tail light, and signal lights. The headlight will be designed in such that it will output at least 400 to 600 lumens and be clear white color. As for the tail light, it will output at least 50 lumens as well as a red color for clear visibility behind the bicyclist. And the signal lights will output at least 50 lumens and a yellow color. The LEDs chosen are all on the table on the right side of the slide. starting with the headlight specification being 3232 volts with 700 milliamps and can produce anywhere from 1600 to 1800 lumens. The taillight requires 2 to 2.2 volts with 1200 milliamps consumption and output 115 to 120 lumens. And lastly, the signal lights, like the taillight, can handle 2 volts to 2.2 volts, but only require 700 milliamps and produce 50 to 60 lumens. All LEDs chosen to accomplish each of the requirements needed for this section. Now entering the LED drivers, they're incredibly crucial for our lighting system in such that they essentially will intake a wide range of voltages and output a steady current needed for the LEDs. Starting with the headlights, the team will be using a step-up LED driver to convert 12 volts to 30 to 32 volts with a current of 700 milliamps. It's also important to note that the LED driver will also contain the option of pulse width modulation dimming for brightness control. This will be utilized since we want our project to range anywhere from ordinary urban city cyclists that ride at night to bicyclists that don't have much street lights or live in rural areas. To the right is the LED driver that will be used for the headlight, which is the LDH45AA700W. Next up is the tail lights, which will utilize an LED driver that can step down 12 volts to 2 to 2.2 volts and output 1200 milliamps. And lastly, an LED driver for the signal lights that can support the same input and output voltages, but can output 700 milliamps. So for the RFID, we went with the HiLightGo RFID kit. This kit includes an RC522 RFIC card sensor module, which can read and write up to 13.56 megahertz contactless communication. It comes along with blank cards and a key ring. It was also found on Amazon for a cheap price of $5.49, which fits within our project budget for RFID selection. It can also use simple SPI interface so that the ESP32C3 can communicate with it easily. And lastly, it only requires 3.3 volts at 13 to 26 milliamps when active, which our battery can handle.
Moving on to the battery, the power supply for this project will be the ECI 12-volt lithium Life PO4 battery, which is $29.99 on Amazon as of this recording. The battery holds a long life at 4 amp hours, which is very much needed for the parts of our project, specifically the headlights, due to how much power is needed for the full brightness. It can be placed inside some form of housing that we'll design to support waterproofing, and this housing will also be easily mountable on the bicycle since itself is only 1.7 pounds. So it's small and compact, which benefits our project aim in reducing the weight of the device, while also being rechargeable, which is highly sought after for in our project for long usability. And we chose this battery over the Amazon Basic AA batteries because overall it's cheaper, more easily rechargeable, and less complex in that we don't need to combine multiple batteries in series to achieve the same voltage. The battery charger is the Smart Charger Lithium Life PO4, the same company that makes the battery, which we figure is a bonus for compatibility. The charge time, even the slow charge time, fits well into our project scope, which was the main selling point. And as another bonus, it has smart LED indicators, which is used to tell when the charging is done, which is both helpful for us and for the users. For theft detection, we're using a PIR infrared sensor that will be placed on the bike to tell if someone walks in front of the sensor. We selected a small Raspberry Pi compatible model that's used by hobbyists due to its low cost, low complexity, and low power. It only runs at 5 volts at the maximum. The idea is to connect this sensor to the main chip that will be able to tell the user when the sensor has been triggered. Moving on to standards and constraints. For constraints, both economic and time, we have the chip shortage. So we have low stock price increase and an increase in shipping times. The chip shortage has been a prevalent constraint throughout these 2 semesters. For standards, we have several communication standards we have to adhere to, so Bluetooth, Lua, TypeScript, and then of course USB-C for the motherboard, I2C and SPI communications. Moving on to our hardware design challenges, we had 3 main ones. The biggest one probably would be the global chip shortage, as mentioned in the previous slide, which there's really no way around it, so we have to find alternatives using different websites, different parts, or just bite the bullet and deal with the shipping times and price increase. The weight and space of hardware, so the PCB takes up most of the space and weight. The battery is also going to be a large sort of brick that will take up a lot of space. We have to find a way to fit it onto the back of the bicycle rack. And of course the battery life, obviously we don't want a battery life that will die frequently, so we have to find a good one that, both a good battery and a good way to conserve power and recharge the battery efficiently. And moving on to the administrative content, which is the final part of this presentation. On to team responsibilities. We have it split up so that the students in the EE department will handle primarily the hardware. As you can see, we have primary and secondary objectives for every student, and the CP students will handle mostly the motherboard and the mobile app, where we have it so that the primary and secondary objectives are split between members so that each member can back up the other one when there's a need for collaboration. As for our current progress, we broke it up into several categories, which were analyzed for the rough percentage of being done. Research and design are mostly done. Part acquisition is almost there. We just have to wait for some things to finish shipping. Assembly and software are lagging behind a little bit, but that's only because of the part acquisition. And then the testing is coming at the very last stage. And overall, as a rough percentage, we are a little less than 3/4 of the way done, but we certainly anticipate being done by the due date. For budget, we had an original high ceiling of $400, which was $100 per student. However, being frugal and shopping efficiently, we were able to get that well under $250. The only thing that would have been difficult for us is the bicycle, but one of us owns it, so we're not counting that as our budget. Everything else was, we would say, reasonably priced. We haven't had any problems with excessive spending. And here we have our milestones. These were originally planned out last semester. However, we found that they have still been useful for keeping up with the goals and deadlines of our project. The only thing that had to be changed was adding, for instance, the CDR presentation at step 13 and adjusting a few dates as we tackle certain problems slightly out of order. But all in all, we're still updating this chart to keep up with our progress. What we have left, as you can see, is just finalizing the building once all the parts arrive and do some troubleshooting. And to finalize, we're looking at our future objectives, which ties into the milestones chart. Specifically, we have to finish our building and testing, wait for the PCB to ship and other hardware to ship, finalize the app integrated with the hardware, do some troubleshooting, which we don't anticipate being significantly time-consuming, and we, of course, build our website and write our final report.